talk about levers in biomechanics, I will start with a job that I saw in Spokane, Washington, an aluminum smelter. And we will first analyze the lever because that's really intuitive, and then we'll analyze the guy doing the job. What he's doing is he's pulling up on this lever as hard as he can. There's a pivot point here. The lever is attached to a vertical rod that goes down to a 400-pound carbon anode that he's trying to press down through a crust. You can even tell from his body posture, he's pulling up on this thing as hard as he possibly can. This is a hard job. It takes a lot of force to force that anode down through the crust. Well, I said this is a lever system, so let's go back and just think about basic levers. Teeter-totter lever system. I got a couple of kids. One's going off to college, so he's a little older than sitting on a teeter-totter with me. But when he was younger, when he was a little kid, right, he might sit out here, and if I sat here, we could balance, even though I was a lot heavier than he was. And the reason was basic mechanics. Now, those of you who are physicists or took physics learned the word torque. Okay? Those of you who are engineers learned the word moment. The purpose here today, they are same thing. Don't worry. When I'm an engineer. I got trained as an engineer, so I will use the word moment as we go all the way along. But if you're a physicist, just every time I say moment, edit it out and put in torque. And this will work. Okay? So the moment generated by my son at the end of the lever is his weight B times the moment arm. That's the key word here. Moment arm. This perpendicular distance from the application of force to the center of rotation, y. You take B times y, and that is the clockwise moment. That's the moment that's tending to rotate this lever clockwise. The counterclockwise moment is my weight A times the moment, my moment arm x, bx. For this to maintain what's called static equilibrium, ax has to equal to by. If that's simple algebra satisfied, just stays static. Okay? And we're going to assume everything here is static because we're not studying baseball pitchers or high velocity stuff. This is kind of low. Most work is low velocity, and we can model it pretty well as statically. However, if you're looking at a job that is really dynamic with high velocity, then you probably want more advanced analysis tools. Okay, everybody okay with that lever? This is all intuitive. Okay. Now let's apply it to this anode job. Let's assume that the hand force is denoted F sub hand. This 30 inches from the pivot point, 3 inches from the pivot point to the vertical upright bar. There's a reaction force F sub crust. We can write down the moment equilibrium conditions as 30, the moment arm, 30 inches times F sub hand is equal to 3 times F sub crust, divided through by 3, and you get 10 times the hand force is F sub crust. What that's saying is the anode is feeling 10 times the force of what this guy's pulling up with. It's a 10-fold force multiplier. You know, the Greek Archimedes is supposed to have said, give me a lever long enough, I can move the world. That's why. Levers are force multipliers. That's why we love them. That's why we use wrenches and levers and all kinds of crowbars and things like that. They're great tools. They're wonderful, right? The only problem is the guy is also a lever system. That's what we're going to do next, now that we have some intuition about levers. Well, Newton said that for every force there's an equal opposite force. So if he's pulling up with F sub hand, the bar is pulling down on him with F sub hand at his hands. I have created what engineers call free body diagram. I've just photoshopped down out his lower extremity. And we will analyze the mechanics of his upper body, which is how you do it in engineering. And we're going to start with the hand force. There's a pivot point of his lumbar spine. Okay? Between the pivot point and the hand force, we'll assume 10 inches from the pivot point to the point of application of this hand force. Okay? Now, I said the erector spinae muscles, the back muscles, on average, I started 2.5, I rounded down to 2 inches. Say 2 inches posterior to the center of rotation. Okay? And I've denoted the muscle force as F sub muscle force, being driven by the hand force. I did the superscript hand force because there could also be a contribution of muscle force that comes from body weight, and other stuff. But we're going to begin with just what's being driven by the external hand force. We write a moment equilibrium conditions 2 times the muscle force, the moment arm 2 inches times the muscle force is equal to 10 inches, 10 times F sub hand. Divide through by 2 and we get 5. This is a 5-fold force multiplier working against him. Suppose he is pulling up, which is totally plausible. When you look at the size of this guy and the posture, he was pulling up as hard as he could. Suppose that he is pulling up with 100 pounds of force. What does the erector spinae have to contract with? Which is? 500 pounds. Muscle contraction force. So the point is that there's the lever system, there's a force multiplier acting against the biological tissues. Now it gets even worse. There is the center of mass in the torso. Let's assume it's 3 inches. So you can do the moment of equilibrium. You end up with, if the mass of the body is mg, okay? The mass is m and g is the acceleration of gravity, so the weight is mg. That the muscle force that's required to maintain just the body posture, that's why superscript with body weight, okay, is 3/2 mg. Not a lot, but the thing is, it adds. These things are additive. The muscle forces are additive. So I illustrate that by putting these vectors end to end, vector addition, okay? Well, actually, you also have to add more because there's also the hand force and mg, the weight of the body. So when you add all of that together, you have large muscle forces. Suppose that I took away this little symbol here, this little triangle, okay, and I had to put all these muscle forces on this free body. What should the free body do? Go down, whoop, disappear. What keeps it from just disappearing, going down, right off the screen? The spine. The spine exerts an equal and opposite reaction force. It's called a joint reaction force. That is equal and opposite to the sum of all of these. The spine is feeling the sum of all of these. Which means that if by lifting that 100 pounds, the muscle contraction force, this component was 500 pounds, his spine is experiencing 500 pounds of compression force, 500 pounds. Then you add his weight. So you're talking, and the hand force, so you're talking hand force, and this is hypothetical, is another 100, so that's 600, you'd be talking, 700 pounds force. Actually, we analyzed this job. It actually was 728 pounds. I just remembered that. That's what came out of the model, okay? So the arm waving actually ended up in the same approximation. The point being is that at the beginning of this, do you think that lifting something would create 700 pounds of compression force of the spine? It's not intuitive to most people. The internal loadings on tissue is very high, and that's why when I was talking about the intervertebral disc, it has a challenge of both allowing motion and resisting a lot of compression.